Now we're going to get into reactions of acids and bases, and since the focus of this class is on the chemistry of life processes, I'm going to take a moment here on this slide. And so your stomach has glands in it that are made up, of course, of cells, and those cells generate hydrochloric acid, a strong acid, as you've seen from the list on the table earlier in the notes and in the textbook. And it keeps secreting that until we get to the proper pH. And so even though it's a strong acid that has a very low pH on its own, it also matters the concentration of it. You can have a watered down or dilute hydrochloric acid. And so it keeps pumping out that until it hits the proper pH for digestion, and then it will start to digest the proteins in the stomach. Of course, not all the digestion process happens in the stomach, and so after that part is done, it then passes on into other parts of the digestive tract. Anyway, here we're going to get into acid-base reactions and how to balance them and do calculations with them. So acids react with certain things. In cartoons and such, you'll see acids just dissolve something completely away, you know, a cartoon character down to the skeleton, and that's just not true. And I've had students who are surprised by that, but I tell them, like, look, here's a bottle of acid. Obviously, it's not reacting with the bottle. Now, interestingly, hydrochloric acid won't react with plastic, but does with glass, but most of my other acids will react with plastics, but not with glasses. And so obviously there's some containers that are resistant to them, but in general, many metals will react with acids, and when they do, they'll produce a salt. That salt would be the metal and the anion on the acid, and then that's releasing the hydrogen from the acid, those hydrogen ions forming hydrogen gas. Bases will, or acids will react with bases to produce a salt and water. The acid and base, if they are of equal strengths and or concentrations, they will neutralize one another, they'll cancel one another out, and because acids are made up of hydrogens and bases of hydroxides, those hydrogens and hydroxides come together to form H2O, and then the other halves of the acids and base, the cation from the base and the anion from the acid, combine together to produce a salt. And then also they'll react with carbonates and bicarbonates to produce carbon dioxide. This is your classic baking soda and vinegar reaction. And so a salt, real quick, is any organic compound that does not have a hydrogen as the cation. If it does, it's an acid, or an OH minus as the anion. That is a base. There are some where it is a oxide as well. Things like rust usually aren't considered salts as well. A lot of times salts are soluble, but not always. So acids react with metals to produce hydrogen gas, and so you can see here it's a single replacement or single displacement reaction, and it will produce a salt and release the hydrogen gas. Notice we have to have some coefficients in here to balance things out properly, because hydrochloric acid here only has one H, but we end up having a hydrogen gas only exist in nature as H2. And you can pause and take a closer look at those reactions if you want. Here we're going to write reactions for these two. So here we have magnesium metal. Of course, metals are solids, and it's reacting with hydrochloric acid, HCl. Aqueous, we've already been told. And we need to predict what it's going to form. Well, as we've seen already, it's a single replacement reaction, so the magnesium is going to swap places with the hydrogen, and we're going to be left with hydrogen gas. It's going to be the same as the other ones, and so I'm going to write that out here, H2 gas. And then the magnesium is going to bond with the chlorine. Well, the chlorine has a 1- charge, or chloride has a 1- charge. Magnesium ion has a 2+ charge. So to have a neutral compound, we're going to need MgCl2. And then because it's doing the weird thing there with the lines across the screen, I'm going to change color here for our balancing. So right now we have one magnesium on each side, so that's good, but we have 2 chlorines here and only 1 there, so we're going to need a 2 coefficient here to balance that out, and that will take care of balancing out the hydrogens as well. Remember, we have to have a balanced reaction. So for our next one, we have aluminum metal, which is aluminum solid, plus nitric acid, so we have HNO3, yields, again, we're going to end up with hydrogen gas, so I'm going to put that one out here at the end. Maybe should have left myself a little bit of space there in case we need a coefficient, but we'll squeeze it in there. And then we're going to have the aluminum swap places with the hydrogen, and so we're going to be left with aluminum nitrate. Aluminum has a 3+ charge, nitrate ion has a 1- charge, and so then we're going to need 3 nitrates to cancel out the charge on the aluminum. So that's going to be NO3, 3, and it will be aqueous as well. Looks like I left that label off up here, but way back when you covered solubility, you should have seen that most halogens, halides are soluble, and all nitrate compounds are soluble. Once again, we're going to need to balance. I'll switch colors here, and so we have 1 aluminum and 1 aluminum, so those are good. We have 1 hydrogen and 2 hydrogen, so those don't match, so I would need a 2 here, but that's not going to balance out my nitrates. So I'm going to need 3 nitrates, and so let's try a 3 here. That gives me 3 nitrates, and now it gives me 3 hydrogens, only 2 hydrogens there. There's no way to make that work, so let's get rid of that. And I found a shortcut is to multiply those by one another, and so we need a 3 for one and a 2 for the other, so multiply those two and you get a 6. Sometimes you end up needing to reduce at the end, but it's almost guaranteed to work. So we got a 6 there, a 3 there, and then 6 nitrates, so we're going to need a 2 here to multiply by this 3 to give us 6 nitrates. That gives us 2 aluminum, so we end up with a 2 here. So 2, 6, 2, 3, and it's not reducible. So there we have it. Anyway, as we mentioned already, acids also react with carbonates and bicarbonates, or hydrogen carbonates is the other way that they're known. And so that's those. And when they do that, they produce carbon dioxide gas, a salt, and water. And so coming up with the products of these, you know it always produces a salt and water, so the water is always there. The carbon dioxide is always there, and then the slightly tricky part is figuring out the formula of the salt itself, and we'll get some practice on that here. So for A, we have magnesium carbonate and hydrobromic acid. And I left off my states of matter. They're up there for the sake of space. I'm going to leave them off. Nope, we need an arrow here. Yields. And then we're going to have water, carbon dioxide, and a salt. Well, the salt comes from what's left, and I'm going to switch colors here to emphasize this. So what's left is the cation there and the anion there, so we're going to have magnesium bromide. Magnesium has a 2+ charge, halogens have a 1- charge, and so that's going to be MgBr2, because we'll need 2 of those to cancel out. Now we've got to do the balancing. So 1 magnesium each side. I've got 2 bromines here, so I'm going to need a 2 coefficient here. That will give me the 2 hydrogens I need for my water, and then you'll notice this is CO3. The carbon dioxide comes from this, and the extra oxygen goes into the water, and that's why I started my balancing with the salt instead of trying to balance out the hydrogens and carbons. I've personally found that it's best to save carbons, hydrogens, oxygens for last. I've also found that when I have something that's in more than one location, like the oxygen being in 2 separate compounds here, they're a little bit harder to balance, so I try to get the other things balanced first and then work through the rest. So this one here was a carbonate. Our next one here is a bicarbonate, and so it's just slightly different, but it produces the same things. Hydrochloric acid, we'll go ahead and do states of matter here. It looks like I left off states of matter on the other one, so I'll go back and fix that here at the end of this one. We're going to produce water, which is a liquid, carbon dioxide, which is a gas. We'll point out if the reaction is exothermic enough, you sometimes get steam, but you almost always get liquid water and some gaseous water when that happens. And then we've got to figure out what to do with the rest. Well, we have sodium here and a chloride ion here, so that's going to be a 1 plus for the sodium, 1 plus for the, or 1 minus for the chloride, and so that's just going to be NaCl, regular old table salt. Because it's in the presence of water, it's going to dissolve, and so that will be aqueous, and I think we might be balanced already. 2 hydrogens, 1 chlorine, 1 sodium, 1 sodium. We've already done the hydrogens, 1 carbon, 3 oxygens, and 1, 2, 3 oxygens. So yeah, we are good there. Coming back up here to squeeze in my states of matter on the products, at least the reactants that was given to us, we have liquid water, gaseous carbon dioxide, and magnesium bromide is also soluble, so it would be aqueous. The last type of reaction we have here is acids and bases, or it labels this here as acids and hydroxides for whatever reason, which gives us a neutralization reaction where the two will cancel one another out. In these, you always have the hydrogen on the acid and the hydroxide on the base form water. I will point out, when it comes to balancing, I think it's sometimes easier to think of water as HOH, and then to try to balance the hydroxides with one another and balance the hydrogens with one another. It just makes the balancing a little bit easier since you have that hydrogen in 2 locations over here, but only in 1 location over here. If you think of it as HOH, I tend to find that works better. And then again, the cation on the base, the anion on the acid are going to come together to form our salt. Because of this, we can write out a net ionic reaction equation for strong acids, strong bases, because strong acids and strong bases completely dissociate. They completely break apart when they dissolve, and then the salt that they produce is almost always soluble, and so then we will have aqueous salts, and at that point we can cancel out the things that are the same on both sides, which ends up being the salt ions, which are considered spectator ions, and we're left with hydrogens from the acid plus hydroxides from the base to produce water as our net ionic equation. This is the net ionic equation for every strong acid, strong base neutralization. It's guaranteed it will reduce down to this. The ones that do produce a solid here, you technically can write a second, or when they produce a precipitate, a second net ionic equation for that, but it is always going to produce this as its net ionic equation. So here we have a balanced equation for the neutralization of solid magnesium hydroxide and nitric acid. I suppose since this is solid, that's why they mentioned hydroxides instead of bases. Technically, it's a base when it dissolves. Anyway, and so we have magnesium hydroxide, that's MgOH2. Hydroxide has a 1 minus charge, magnesium has a 2 plus charge, solid. Nitric acid is HNO3. You can go through the naming process, telling you there's a nitrate ion and the with the ic acid suffix, the nitrate polyatomic ion, and then of course acids have a H there. Since this is an acid, it's going to be aqueous, it's going to be dissolved, and then we're going to produce a water, H2O, and a salt, which here will be magnesium nitrate. Magnesium again has a 2 plus charge, nitrate has a 2 minus, or a 1 minus charge, so we're going to need 2 of them. The water, of course, is a liquid, and the nitrate is aqueous. And I apologize for all those straight lines. I know they get in the way a little bit. I wish I knew why my tablet was doing that. Anyway, at this point we need to balance it, and so I'm going to change colors here. We have 1 magnesium on each side, but we have 2 nitrates here, and 2 nitrates over here, or 1 nitrate over here and 2 over there, so we're going to need 2 here, which is a 2 coefficient. We have here 2 hydrogens now, and 2 hydroxides. Recall just a moment ago I said it's helpful to think of this as HOH. I have 1 hydrogen and 1 hydroxide here, and so then I'm going to need a 2 coefficient here to balance that out. If you wanted to balance it out individually, then of course we have 4 hydrogens here, and so then we would need 4 hydrogens over here, and so we need a 2 coefficient to multiply by the hydrogens. The oxygens and the nitrate are already taken care of over here. We have 2 leftover oxygens here, and so the same 2 coefficient would balance out our oxygens as well. These 2 here are multiple choice of the same thing, so again, I like to think of the waters as HOH. And so in this case, I've got everything looks to be balanced so far until we get to this hydroxide. There's 3 hydroxides, so I'm going to need a 3 coefficient here to give us 3 hydroxide. So that gives us 3 hydrogens, so I'm going to need a 3 here. That gives us 3 chlorides, which gives us a 3 there. We have 1 aluminums. We're good to go. So we don't write those invisible ones normally, but for the multiple choice, they've listed them here. And so we have a 3113, that's going to be this one. As a side note, when I write the multiple choice questions, I would write this as 3 blank blank 3, or I would just pick one of these 2 coefficients, and I would say, when you balance this one, what is the coefficient in front of one or the other? Because if you have the correct coefficient there, you've got to have the whole thing balanced already. Anyway, this next one here, a little bit trickier for me to do in my head as I look ahead here, but where did my pointer go? There it is. HOH is what I think of this as. So let's see here. 1 barium, 3 barium, so I'm going to need a 3 here. That gives me 6 hydroxides, so I would need a 6 here to give me 6 hydroxides. That gives me 6 hydrogens, so I'm going to need a 2 here to give me 6 hydrogens, and then 2 phosphates and 2 phosphates. So 3, 2, invisible 1, 6, 3, 2, 1, 6, that's going to be B. So this brings us to acid-base titrations. Titrations are a process to determine the molarity of an unknown substance. In this case, we're going to do an acid. And so what we do is you have a known volume of an acid down here, but a question mark on the molarity. And then we're going to be adding into it a known concentration of a base, and we will be measuring what is initially an unknown volume of base for the 2 of them to cancel out. And then usually we use a pH meter or an indicator to measure where the endpoint of the titration is. Personally, I usually use both. The indicator gives me a visual confirmation, and the pH meter gives me the specifics. But what happens is, as you pour in the base into the acid down here, you really want to drip it in and not actually pour a lot. We use a piece of glassware called a burette up here that allows us to, 1, measure this volume very precisely, and 2, really control and put a nice slow stream of drops down here to make sure that this thing just neutralizes completely as we go. So again, before the reaction starts, we've got the base up here. We've got an initial volume in here, and so you would read this volume. As we pour it in, the volume is going to go down, and once we neutralize this thing down here, we'll have a new volume, and when we have that new volume, we'll measure it there. And then the difference between those two is, of course, the amount of base that we actually use there as we added it to a known volume of an acid, but the concentration here, again, is unknown. Up here, we would know the concentration, and we would be measuring the volume. And so you can see here that as the phenolphthalein starts to turn pink, we know that we're nearing the end point of the titration, and when we actually get there, it turns completely pink. And we know at this point that the moles of the base are equal to the moles of the acid. And since we know the concentration already of the base, then we can use the volume to calculate the molarity of the acids. I didn't list it here unless I skipped over reading it, but we also knew the volume of the acid. And so we can use the neutralization equation of the values that we have there to do this. So we're asked here on this problem to solve for the molarity of the acid if 25.5 milliliters of the sodium hydroxide, and the sodium hydroxide has a 0.438 molarity, is required to neutralize 0.0250 liters. I believe this example is also in your textbook, or at least there's a similar one, in that they list their own set of steps. I'm going to not label those steps as I go here. It's the same process, and then I will also show you a shortcut process for doing this as we go. I also like to do my calculations in one step rather than doing multiple steps as I go throughout the doing a step, getting an answer, doing a step, getting an answer. You'll see what I mean as I go here. And so we'll work this out the stoichiometry way. So I have 0.438 molar in AOH. Well, molar is, of course, the same thing as moles per liter. And so then we need to get rid of this liters because we know the moles of the two, the hydrochloric acid and the sodium hydroxide, are equal. And so to get rid of that liter, I know that 1 liter is 1,000 milliliters. That's one of your metric conversion factors. And I know that I've used 25.5 milliliters of sodium hydroxide. And so then this is going to cancel out our milliliters, our liters, and we're down to moles of sodium hydroxide. Well, we know that the moles of sodium hydroxide is equal to the moles of hydrochloric acid in the reaction, and for the specific mole values here in the reaction, we need the coefficients there, and so it's a 1-to-1 situation here. So we have 1 mole of sodium hydroxide is equal to 1 mole of hydrochloric acid based off of the coefficients in the reaction. We now have these 2 moles being equal, and we've canceled out our moles of sodium hydroxide, and we're down to moles of hydrochloric acid. We want the molarity, which is it dissolved, not the moles, and moles, of course, is moles per liter, and so we need to divide this by, and I'm going to do that by putting a 1 over the liter value here. If that value had been given to you in milliliters, then obviously you would have to do one last step to turn it into liters. Of course, if this here had been given to us in liters, again, we could have skipped this conversion step as well. But this will give me moles of HCl per liter of HCl, and so then that will be our molarity. And then I multiply everything in the numerator, 0.438 times 25.5 times 1 times 1 times 1, which I don't need to do, and then I do it divided by parentheses everything in the denominator, so 1,000 times 0.025, and I get 0.44676 molar HCl, which is the wrong number of significant figures. Let's see here, we've got 3 here, 3 here, and 3 here, and so I'm going to round my final answer to 3 as well. So 447 molar HCl. As a side note, rather than looking at the sig figs of everything, you could look at the sig figs of just this one here, as we really want to match the certainty that we had on the original. And so if we can make it look like that, then we're good. I will also point out that these 2 volumes are very close to one another, and since this is a 1-to-1 ratio, I would expect their concentrations to be close to one another. In milliliters, this would be 25.0, and so since they're the same number of moles, and they're very close in volumes, I would expect their molarities to be very close. It's just a quick check of your answer. As I said, there is a shortcut way to do this. It involves using a formula that I don't think your textbook mentions here. It's possible you came across it when it came to diluting solutions, but it works for this as well. And so the molarity of your acid times by the volume of your acid is equal to the molarity of your base multiplied by the volume of your base. And so then we have an unknown molarity for the acid. The volume of the acid was 0.025 liters is equal to the molarity of the base, which is the 0.438 molar, and that's going to be multiplied by the volume of the base, which we need to be in a matching unit. So I'm going to have to do this convert to liters step. That's divide by 1,000 or move the decimal over 3, so 0.0255 liters. And now I'm going to divide both sides by the 0.025 liters. These are going to cancel out. The liters here are going to cancel out, and we're going to be left with molarity for our units, which is what we want. That's going to give us then a molarity of the acid that is equal to, notice, 0.438 in the numerator, 0.0255, which is this one here, 0.025 down to the denominator, and this here came from converting that decimal, so we can ignore that. And you'll notice the numerator and denominators down here match what they were up here, so we're going to get the exact same answer. I'm going to go ahead and round it off and not worry about retyping into my calculator. If you want to prove that to yourself, you can take a moment and punch this into your calculator and prove to yourself that it does come out to be the same answer. Like I said, I don't think your textbook mentions this one. It's a formula I was taught. I will say that if you have a acid that has a 2 subscript here, or a base that has a 2, or some other subscript there, there's an extra piece to this form you have to do. You have to account for that number of moles, and there's 2 ways you can do that. I would say that it's easier to go through this method when that one doesn't work, rather than worrying about the 2 versions of the formula. And again, coming back to health, your stomach produces acid. Sometimes it overproduces acid, or that acid leaves the stomach where you have the protective lining and ends up in the esophagus. And so to do that, we want to neutralize that excess stomach acid. And so to do that, we will do antacids, and the acids usually have hydroxides in them. Aluminum or magnesium hydroxide are your most common ones, and then they will neutralize that acid, but they use ones that are not very soluble, so that you don't get really high pHs of hydroxide in there, which would also be damaging. And so we neutralize a strong acid with a weak or not very soluble, or both, base, and that's your health link there. And there's a list of antacids and their components if you want to take a moment to look at them.